But anyway, hi, I'm David. I'm a software engineer at Meta, and I do big data stuff. I've been doing big data stuff for most of my life. In fact, my very first talk here at NDC, like 13 years ago, was about NoSQL databases, and that's pretty much what I've been speaking about and doing at work most of my time. My last talk here at NDC was about big data for software engineers, which is how data warehouses work, how data lakes work, really like industrial grade heavy data infra, which is cool, but I'm guessing that most people don't really do and use those tools every day. And so this year what I wanted to do is talk about stuff that most people can actually go and use at work. And it will be data tools, analytical data tools that are actually going to be useful for most people, even if you don't work at a company with, like Meta, which has ridiculous amounts of data. And so that's what we're going to be doing talking about today. So when I say big data, so how many people here actually work with data a lot of the time? Like you run queries, you query data, stuff like that? Pretty much almost everyone. That's nice, cool. But I'm guessing most people aren't really working with petabytes of data most of the time. If you are, great, that's very cool. But most of the time, we're going to be using something else. And so when I say big data, everyone probably has a different idea of what that is in their head. And so I want to kind of align us on what we're talking about so that we can talk about stuff that isn't big data, but is still very cool. And so big data depends who you ask. I kind of paraphrase the quote from Wikipedia. But for most people, big data would be a field of IT where you work with amounts of data that you can't really work with using traditional tools. So your SQL Server or Postgres or Microsoft SQL Server, you can't just use your everyday database to do certain tasks. Usually, and in the context of this talk, is analyzing a lot of data, so analytical tasks. And when I say analytical, I mean unlike normal work with databases where you put in data and you read in data, analytical queries usually touch a lot of data and try to aggregate a lot of data all at once. And so when we say big data, we mean tools that are used to work with data that are too big or too complex for your everyday normal tools like databases that we'll know. Now the thing is, most companies don't really have big data in that context, right? There are a lot of companies which have gigabyte scale data, which is like every day. Gigabytes is easy, I can do that on my laptop. There are significantly fewer companies which work on a terabyte scale, where you actually work with terabytes of data normally. And there are very, very few companies which work with petabyte. Like I work in one of the few companies in the world that are on the exabyte scale. Meta has more than an exabyte of data, which is a million terabytes or a billion gigabytes. So there's Google and a few others, but most companies don't usually go to the exabyte scale. But even that, even when you have exabytes of data on a day-to-day basis, I don't touch an exabyte of data every day. Like when I go and I run a query, when I want to do some hypothesis about user behavior, usually I'm going to touch a very tiny fraction of the data we have. And so I don't really need data infra, which is meant to work on an exabyte or a petabyte of data. I need something that will get my specific workload done quickly. And if I can do it on my laptop instead of using some large infra, that's even better. Okay? And so there are a lot of statistics that have been done in recent years on what does a typical query, analytical query, actually do. And statistically, most queries touch somewhere between 1 and 100 gigabytes of data. And this is a statistic that Gartner have done, and there's a few other statistics companies which have actually went to a lot of customers and looked at what are typical queries in a typical company. And they're all in that 1 to 100 gigabytes range, which means that you don't actually need heavy industrial data infra to run these kinds of queries. Like if it's 100 gigabytes, I can do that on my laptop very easily. I have 2 terabytes of storage on my laptop and a huge monstrous CPU, which isn't actually being used most of the time, and a huge graphics card, which, unless I'm playing games, isn't really being used most of the time. And so why do I need to spin up and maintain and pay for a very complex data infrastructure with a data warehouse and some Apache Spark or EMR or some very complex tools to set up, if I can do the equivalent of that just locally on my laptop? And this is what this talk is about. Because in the last few years, we've created a lot of tools which address this specific niche. It's somewhere between big data and small data, so like something you can do on a SQL Server, which there's not a good word for it, but like medium data, right? Medium-sized data. And one of the other reasons why we need this kind of medium-sized data is there is a phenomenon in the industry that has existed for a long time, but it's become very, very strong in the last 20 years, which is that the speed at which organizations collect data is much higher than the speed at which they can actually do something with data. Right? I think intuitively you can all understand, like, think of the best use case for this is logs. Everyone has applications logs, right? What do you do with logs for your microservices, whatever you have? You store them somewhere else, and then you very rarely look at them. Most application logs aren't useful because there's going to be stuff like transaction completed, 200 OK, right? That's not useful data. You're never going to do something with it. Mostly you want to have like the 1% of logs that have something interesting, anomalous, like an exception or a warning or something like that, right? And so most of the data you collect is what's called dark data, which is data you just store and never use for something valuable ever again. Which is why, when we work with data, we actually want to work with the relevant parts of data, not everything. And so even if you have petabytes of data collected, usually you're going to be working with something that's much smaller than that. And so if you want to redefine what medium data is, it's going to be something that's too big for traditional data applications, but too small to justify actually using big data infra. Because big data infra is very complex. I spent a large part of my life spinning up systems that actually work with big data, from Hadoop in like 20 years ago to whatever we have right now. And it's expensive. For a relatively small company especially, which is mostly focused on time to market and getting a product out at the door, pausing everything to spin up whatever, so Apache Spark, and learn how to use it and set up a data warehouse is an investment of time and effort they really can't afford because they need to be focusing on actually getting the product out and shipped to customers. And so if we can actually find something that is in this medium data range, that'll be a really good thing. And so in the last few years, the industry has come up with a bunch of medium data tools. Tools that are good enough, easy enough to use, very easy to set up, very low learning curve, but are in that range where you can go and analyze a terabyte or 10 terabytes of data reasonably easily without spinning up, like a Hadoop cluster or a Spark cluster, or paying someone like Snowflake for a large warehouse where you have data warehouse where it's easy, but it's also very expensive. And so we get to the point of this talk, which is DuckDB. DuckDB is one of a very few tools, but numbers growing, that is meant to work on a single instance on your laptop, but of a powerful machine, right? It is built to be very scalable, very easy and portable. It's one file. You download one file and it just works. It's very extensible. It's open source. You can download it. It's easy and free. And it's built to maximally utilize all the resources on one machine, so on your laptop, right? And then what it does is it runs big data analytical queries with the maximum possible efficiency on that one machine, which means it can do a lot more than your typical database with the same hardware. But obviously, it doesn't scale to what we can do with, with Apache Spark and 100 machines and so on. And so it addresses this little medium piece of the data infrastructure. And so where does it fit? There's a bunch of different ways to classify databases. Like my very first talk here at NDC was about classifying different types of databases and what they do. But specifically, we're all familiar with embedded and standalone databases. So standalone databases, I'm sure you all worked with them. They're your Oracle, MySQL, Postgres, MongoDB, Couchbase, all of these databases, which are meant to be just an application you install. It might be very complex. You can spin up a huge cluster of it. It might be expensive to maintain. It might be very simple. Just spin up a Docker container with MySQL and it just works. But it's a standalone application that does everything for you. It's the full ecosystem. It stores the data. It queries the data. It backs up and all that stuff. And within this range, the two quadrants are transactional and analytical databases. So transactional databases, I'm sure everyone is familiar with, right? It's your standard database that you use for your application, right? It's the backend of your application. You put in data, you get the data out, right? So transactional databases are optimized for typical application use cases. A lot of users, high parallelism, but each query touches a small amount of data, right? You insert one record, you get out one record, or you query something and you look for one record. Because that's the backend of your application. It usually looks for a small amount of data. So analytical databases, on the other hand, which we'll get to in just a second, are built to work with a lot of data in aggregate, right? So there are a few examples, and we'll talk about them in a sec, but mostly what they're meant is not to be the backend of your application, right? They're not optimized for high parallelism, for small queries which touch a little bit of data. They're optimized for a few very big queries which touch a large percentage of your data and aggregate it very efficiently and give you back the results. So if we look at those, there's a bunch of them like Redshift and Amazon and Snowflake, which is a big ecosystem of data warehouse, and a few others. And they're meant to just be an application you set up. It's very complex, but you do it once, and then you pay for maintenance and upgrading and so on. And then you just use it to analyze any amount of data, as long as you can pay for it. The other classification, though, is embedded databases. And embedded databases are very interesting because most of the time, we don't think about them. The one here, I'm sure everyone's familiar, which is SQLite. Anyone here worked with SQLite at all? Like, a lot of people, nice. So SQLite is by far the most popular database, if you just count installs. On their webpage, they have an estimate which says that there's 1 trillion SQLite instances in the world. If you think of it, that makes kind of sense. SQLite is the backend database for pretty much all the web apps, all the browsers. Everyone here has a phone in their pocket. There's roughly 4 billion phones in the world, and there's a couple of hundred applications on every phone. Each one has a SQLite instance. Do the math, it's about 1 trillion installs of SQLite. So it's by far the most used database, but most people don't really think of it as like a database, right? Because it's just a file you put in your application, you import it, and it's done, it's there. And there's a few others which are useful for very small applications where you just want to have a database, you don't want to install it, you don't want to mess around with it, and you just want to get something done very quickly. But the last quadrant of this table is very empty, and it's been empty for a while until just a few years ago, because actually having an embedded analytical database wasn't something we actually needed. Until recently, where we got to this medium data area where we actually need to do analytics on enough data where you can't just do it with SQLite, because that's not going to perform. And you still want to run it, for example, as part of your Python data science stack. I have a bunch of Python scripts with pandas and all these cool libraries which do ML and AI stuff. And I want to use data in there, but I don't want to go to my big data warehouse, even if I have one, right? And I want to just do it in process. I want to be able to run some analytical queries, process the results in pandas, maybe visualize them, maybe train a model on it. And so embedded analytical databases weren't really a useful thing until just very recently, the last few years. And that's what brings us to DuckDB, which is where DuckDB lives. It's an embedded analytical database. You can use it from the command line, which we'll do in a second, or you can put it in your application in process, and then it will create a new database file, which is just one file, and run whatever queries you want and provide this analytical capability. There's also Kuzu, which is even newer. It's like from the last couple of years, which is a graph database, which I think is going to be my next talk next year if I get accepted, because graph databases are just really cool. But that's not the point of today. So this talk is going to be very hands-on. So we're going to do a lot of demos, and that brings us to the first demo here. We're going to be writing a lot of queries. I hope everyone here likes SQL. SQL, by the way, actually, just as a side. It's not SQL, it's SQL. I used to laugh at people who said SQL, because I thought they were weird Americans. But no, SQL is actually the right way, because the name of the query language originally was SQL, the word, because it's the sequel to a previous query language. And so it's actually SQL and not SQL. I was wrong for about 20 years. Anyway, so the first demo, before we get into the actual demo, there's a really popular data set in the industry called TPC-H, Transactional something committee. It's a standardized data set for database benchmarks. It simulates your typical e-commerce company. It comes with a bunch of data pre-generated, and it's used mostly to benchmark across different databases. It comes with a standard set of queries that you can use to measure performance. And what's convenient is that most databases come with TPC-H or something that generates it, and so it's very convenient to have the same data model and the same data you can use for every other database you can try. And so that's what we're going to be using today. We're going to be using TPC-H, TCP-H, for all of our queries. And it has a bunch of tables. It has orders and line items and users and a few other tables, which have just pre-generated data in them. OK. Let's go to the demo. Everyone can see it? Is it big enough? Good. So DuckDB, it's just this file, right? One file, about 50 megabytes. That's the entire database. You can also actually use it as an import, which we'll see in one of the other demos. So let's run it. That's the database. I didn't need to install it. I just downloaded the file and ran it. That's my database. That's a very handy command, because then it shows you the timing of all the queries. OK, so normally, I would be typing, and I found that I usually make a lot of typos. And so instead of typing, I actually saved all of my demos. And so I hope you'll forgive me that I actually will copy-paste instead of trying to type, because otherwise it will take way too long. So we're going to load TPC-H, and we're going to generate some data. What this does is it generates our data model, show tables. There we go. That's our e-commerce company. We can look at how many of there are. Line item. See, that's why I shouldn't type. So it generated 6 million records, right? That was actually very fast, because you'll notice I open the database. It's all in memory right now. So everything is very fast. We have a bunch of data, and we can try to run some queries. So let's run a few queries. First of all, we're going to see if we can store this data, because it's a database, so let's store it. So we're going to export this database. It's going to take a second, because it generated 6 million records across multiple tables, so it's going to be 7-ish gigabytes or so. And what I'm doing is I'm exporting the database to disk in a bunch of different formats. And so we'll look at the formats in just a sec. LS. OK, so now we have. So we exported this record, and in raw format, in CSV format, it takes about a gigabyte. We'll talk about columnar formats in just a bit, but I exported it in a raw representation. So if you go into DB, it's just a bunch of CSV files. Right? That's how data normally we export. We will probably use either CSV or JSON. Like, it's very convenient and human readable. The other two is in a format called Parquet, which we'll talk about in a bit, but it's a much more compact format optimized for queries. And you'll notice that, of course, like I said, the raw format is much less efficient, and the compressed formats are much tighter. And that's one of the abilities we have, which DuckDB can understand pretty much every common database format. So going back to our database, let's run some queries on this data. So we have our timer on, and you'll notice that whenever I run something, it shows us how much time it actually takes. This was 32 milliseconds of actual wall clock time. A lot more CPU time, of course, but just 32 milliseconds to run this. You remember that we were actually analyzing a table with 6 million records, right? 6 million records in a relatively complex query, which does aggregations, sum on something, and group by. That's a heavy query, right? So like, we're doing 3 very computationally expensive things here, right? We're doing aggregation on sum, and we're doing group by, and the query itself. So on a normal database, this would obviously take a lot longer. And this brings us to what's special about DuckDB, which is it's optimized to run these kinds of queries, analytical queries, which take a bunch of data and aggregate it and analyze it very quickly in memory, all on one machine. So let's take a slightly more expensive query. We'll do a join. Joins are notoriously expensive, and we'll see that this join is also very quick. Sorry, that was not the right one. Oh yeah, it is. So we're doing sum and count on a join between 2 tables. And this is taking like a 6 million row table and another 6 million row table, connects them together. Again, still very, very fast, very efficient. Everything happens in memory. Let's do something even more complex. This is a pivot query. For those of you who are less familiar with like the more esoteric syntaxes in SQL, what pivot does is, everyone familiar with pivot tables in Excel or spreadsheets, right? Where you group by some field, and instead of having all the grouped fields as columns, as rows, it pivots the table and puts them as columns, right? So what's going to happen is we're going to group on the date and also on the return flag, but then the return flag becomes columns, right? And so we're aggregating exponentially. So we're aggregating all the columns and all the rows. This is a very expensive analytical query, and obviously it runs in very few milliseconds, and we get the results very quickly. Now, the interesting part, of course, is, let's do another one just for fun, something even more complex. This is your very typical analytical query. We're doing a join on two tables. We're doing group by, a bunch of things. We're doing order by. So pretty much every expensive computational operation we can think of, putting into one query. And of course, this is going to run, again, in slightly longer, so 130 milliseconds. But what you're probably thinking is, OK, well, great, but it's like 6 million rows. I can do that in MySQL. And you're right. You can do this in MySQL. It's going to be more or less the same. So let's go slightly higher. I happened to have a database I prepared, which is a little bigger. It's called HugeDB, and it's 43 gigabytes. It took a while to generate. So let's see how big it is. It's 1 billion rows, almost exactly. It was very hard to generate exactly 1 billion. I tried to make it exactly 1 billion, and it didn't manage. So it's just slightly more than 1 billion rows. And the other tables, like it's also equally large, so like 500 millions. And so let's try the same query we had earlier on a database with 1 billion rows. It's obviously going to take longer, but not that much longer. So it's doing the group, and then it's doing the pivot. And yes, it's taking a little while. Now, if we tried this on MySQL, and I tried it exactly like this query with this data on MySQL, I could go, get some coffee, run around a bit, come back, and it would still be running. And that's assuming it didn't crash because it ran out of memory. So this ran in 15 seconds. It aggregated and pivoted 1 billion rows, all on my laptop. I'll admit I have a pretty monstrous laptop. But still, what DuckDB did is it utilized pretty much all of the capacity of my CPU and the memory. But as you can see, in 15 seconds, we did something that really wouldn't be practical to try and do on a typical MySQL database. You certainly wouldn't want to try it on a production database. And you certainly wouldn't want to try it on a production MySQL database that other users are using at the same time, because they would all lose connection. Let's try, just for fun, the other heavy query. It's also going to run, as I'm sure you're guessing, reasonably fast. It's going to take a couple of seconds to run. But yeah, so as you can see, this is actually doing join between a table with 1 billion records and a table with 150 million records. That join in memory, right, is ridiculously expensive. It's like one of the more computationally expensive operations you can run. And as you can see, it runs in 13 seconds. It actually is faster than the previous one. I'm cheating, obviously, because now a lot of the data is cached in memory, and so a lot of it's pre-computed. And so the more queries you run on the same data set, the faster they're actually going to run, because DuckDB takes advantage of caching on the system level and on the DuckDB level as well. So last thing before we move on, how many people are familiar with explain statements in SQL? OK, interesting, because when I said how many people run SQL queries, it was almost everyone. Here it was like maybe a quarter of the people. OK, so great. Explain, every database, everything that runs SQL has a statement called explain. What it does is it explains what it's going to do for the query. It actually goes and runs the query, but just the optimizer part of the query, and it tells you how the database engine is going to execute the query. So if you add explain before any query, it's going to actually tell you how it's planning to execute it. If you do explain analyze, it's actually going to run the query in practice and then also count all the timings. So let's run this with explain analyze. It's going to obviously take a few seconds, and then the database is going to show us the execution plan of the query, telling us exactly how it actually ran it in parts, like what are the relevant steps of the query. So in this case, it's actually going to give us a very nice, cool table. Now, we can look at the table, but there's actually a nifty tool that shows it for us visually, and I already prepared it in advance, of course. And so this is how the database executes, if I can just manage to do this without embarrassing myself. There we go. OK, these are the steps of actually running that query. Let's go all the way down to, what am I doing? Actually, just click here. Very good. OK, so the way the database, and this would be true for any database, executes this query, is there are two parts, right? Because we're joining two tables. So the first thing it does a table scan on the order table, and a table scan on the line item table, because we're joining those two tables, right? And table scan is, of course, the most expensive operation in databases, because it literally does what a table scan means to you, which means it scans the entire table. It just goes and reads every row in the table. And so this one returns, as we can see, 250 million rows, and this one returns 1 billion rows. And we can see that this is by far one of the most expensive operations. This takes 15 seconds. Now you have to ask yourself, why does this take 15 seconds if the total query was 13 seconds? Well, the timing is cheating, because 13 seconds is the wall clock time, is how much time we actually waited for it. 15 seconds is the CPU time, how much time the CPU across all the different cores actually spent on the query. And so this was 15 seconds of actual CPU time across, I think, 8 cores. So obviously, in real-world time, this was like 3 seconds. Then we do projection. Projection is taking the result of a previous step and just getting part of the records out, or transforming the records. And then we get to the really expensive part of it, which is the join. Right? So there are a few join algorithms in databases, which like it's a whole area of research in itself. But generally speaking, the most common join algorithms is hash join. The way it works is we build a hash table from one of the tables, a lookup table, right? So dictionary, everyone's familiar with dictionaries. So we take the keys from one of the tables, usually the smaller table, and actually create a hash table from it in memory. And then we scan the other table and look up every key in the table. And every key that matches, that's one of our matched results. In our case, because the join is going to produce the full Cartesian product, every key is going to match, right? And so the hash join is the most expensive part. You can see it takes almost 1/3 of minutes, again, of CPU time. In real time, it was much less. And this is where actually the heavy lifting comes. And then it takes the results and does a bunch of things on it. So more projection. The last part is hash group by. So again, we got all of our joins from the tables, and now we have to group by another column. And so how do you group by? There are, again, a few algorithms to doing group by in SQL. Hash group is exactly as the name implies. We build a hash table for every group, so like a key for every unique value of the group. And then we run over all the results and assign them to the correct hash map under the key. And this takes about 43 seconds of CPU time. And then everything else is very cheap, and we get our result from the query. And so this would work exactly the same way in any database we ran, because this is the most optimal query plan you can build, right? So if I tried it in MySQL or Postgres or SQL Server, any one of those, this would do the same thing, except it would take roughly 10 times longer, because it's not optimized for all of those exact operations. Pretty much everything we saw here happens in memory, and it's going to use up pretty much all of your memory, as much as you can give it. And again, like I said, DuckDB is optimized to take maximum advantage of all of your available hardware, because it's assuming that it's running pretty much by itself on your machine. The whole point of it is, if you want to run analytics on your laptop, presumably you're only running one thing at a time. OK. So going back to summarize what we talked about, DuckDB is specifically optimized to run very quickly on one machine. What makes it so quick? It's native. It's built in C11. It's doing most of the work in memory. It automatically, when you load data, when you create data, it actually automatically creates a bunch of indexes for us in memory Normally, in a database, you don't just like the database to create indexes for you automatically, because the indexes in databases are expensive. Every time you add a new record, it needs to go and update all the indexes. So the more indexes you have, the more expensive it is to add new records. When it's in memory, in an analytical database, indexes are very cheap. You can actually maintain the indexes in memory. When you close it, everything goes out of the memory. It's highly parallelized. We haven't looked at it because I didn't find a good way to show it, but it maxes out my CPU to 100%, all the cores, all at once. And it's optimized for taking advantage of vector instructions and data parallelism on the CPU level. So it's actually doing like the most it can do to get the fastest results possible. Again, on one laptop. There is no way to scale out beyond one machine. Like DuckDB is very specifically not trying to solve the problem of scaled out queries. There are a bunch of other big data tools you can use. So if what you want to do is actually scale out to, to multiple terabytes to petabytes of data, this is not the right tool. Right? You've stepped out of the realm of medium data and stepped firmly into big data, and you have to use big data tools. But as long as you can actually do this on one machine, what DuckDB does is it pushes the boundary of what is actually possible on a single machine, on a single laptop, or your server, or whatever it is you want to do. OK, but we talked about DuckDB being an embedded database, not just a database, right? And so the cool part is you can actually run it within pretty much any application in any query, in any programming language. Most of the time I do it in Python because Python is like the universal language for data science. And pretty much most of my work that has to do with data, I'm going to do it with Python because there's a whole bunch of cool libraries to do stuff. Any of you who were at Dylan's talk yesterday, at the end of the day, and he talked about how we don't think of like the nuts and bolts of the tools we use until the nuts and bolts actually break. This is the right example. Like Python has the most nuts and bolts you can use. And most of the time, you can just use them and they work until they break. OK, so let's take a look at a cool Python demo. Obviously, everything is prepared in advance. OK, so I don't know how many of you are. OK, let's do it the other way around. Who here actually writes Python? Nice. More than half the people. Cool. And so you should, most of you are familiar with just Python notebooks. This is the simplest notebook you can have. Those who aren't, Jupyter Notebook is like a very cool interactive way to write Python. You should try it sometime. And so what we're going to do is we're going to run DuckDB in process in Python to do some heavy lifting for data, and then use the results in our Python processing pipeline. Imagine we're training an LLM on this or something, whatever the hype thing is today. Anyway, so all we do is just import DuckDB. That's it, we're done. Just like installing it was, let's copy one file and run the file. Using DuckDB from an application is import the database. That's it, you have a database in your application. We create a new connection, so it will create, if it doesn't exist, it will create this database. If it exists, it will open it. Right? So we open a database file, and then we just run the query. This is the same query we ran earlier, right? So let's run this. Boom, it actually works. That was the database we created earlier with 6 million, not billion, 6 million rows, right? So this works exactly as you would from the command line. That's all the code you need to actually start using an analytical database in your Python code. And it's slightly more code to use it in C++ or .NET, but not a lot more, right? OK, so that's nice, but let's do something more interesting. So how many people, of those who are using Python, who used pandas for something? How is it more people who use pandas than the people who said they use Python? Seriously, there were more hands this time. OK, not getting into that. Anyway, so pandas is a data processing library in Python, by far the most popular data processing library. It's very cool, it has a ton of functionality built into it to actually manage data and group and aggregate and sort and all that. And the cool part is DuckDB can treat a pandas data frame, which is the data collection for pandas, as just another table. We can use any variable in memory and run queries on it. You'll notice that we create a pandas data frame, which is an object in memory in our process. And then we just use it from a query. No setup is needed. I just use the pandas variable name as a table, and it just works. Boom. Okay, so the integration is super seamless, right? The reason is that people who actually write queries don't want to maintain and know stuff about the database. You can just use the database as you would a framework, and it just kind of magically works until it doesn't. OK, so that was cute, but let's do something more interesting. This is our pivot table. And let's take our pivot query, which does all the analytics, and actually export it into a pandas data frame. So what it does is here, this returns the result of the DuckDB query as a pandas data frame, and then we can actually use that result as a pandas data frame object in memory and continue actually processing this data, apply algorithms to it, and so on. So let's run this. And of course, we can see that that's the result of the same query. And now we have it in our Python application as an object in memory. And now we can treat it like any other Python object in memory. So we can, for example, plot it. Right? But the people who aren't using Python, I hope this is blowing your mind, right? Because this is actually one line of code to actually generate a graph from an object in memory, right? The first time I did it, that blew my mind as well. Everyone who's used to it is like, yeah, it's easy. OK, so we took the result of the query, and we just plotted it on a graph. And of course, we can do like more interesting stuff, like we have our pandas data frame here, right? df is the pandas data frame in memory of the process. And we have our line item. This is a table in the database file we opened. We can just join them in a SQL query. You don't need to do anything. You can just join an object in memory to a name of the table, and it just works. You can join one to the other. So you can manipulate data very seamlessly. You can manipulate it across files, tables in a database, variables in memory, remote data sources, which we'll see in a bit, and just kind of treat all of them as names in the same namespace, and just kind of join all of them, copy data from one to the other. Super convenient. You can run a computation and export it directly into a table in the database, or to a remote file somewhere in S3, whatever it is. So it's just a really useful tool to connect all the different data sources in memory. And this is why a embedded analytical database actually makes sense, because it connects all the different pieces which couldn't connect until now in a very easy package, and it does it in a way that's actually very performant, right? In theory, I don't need DuckDB to do this. I could do exactly this code and run this SQL query just in pandas. It would just take about 20 times longer. I tried it on the same amount of data using just a pure pandas query to do the same pivot table. Takes roughly 20 times as long as doing the same thing with DuckDB. Because again, pandas is a Python library. It's not going to take advantage of all the different optimization tools that DuckDB is doing. OK. So we're going to jump straight into the next demo. And for that one, I am going to have to go back to a command line. So we talked about the fact that we can take data from different data sources. But what does that actually mean? There are, I don't know, dozens, hundreds of ways of storing data today, right? If I ask you, I'll give you a list of users, and you should store them somehow. Every person here is going to come up with something slightly different. You can put it in a database. You can put it in an Excel file, in a CSV file, in JSON. You can put it in a queue. There's like a million ways to store data. And DuckDB can read and write to all of those million ways. So let's try a few interesting things. We have an Excel file with a bunch of data in it. That's our Excel file. Wish I could make it bigger, but we'll skip that. So let's say we want to use our Excel file or CSV or whatever way you get data from somewhere else and actually run some queries on it. So we're going to start by just, OK, I'm not going to copy that. That's ridiculous. Of course, that's why you copy and paste. See, that way it works. OK, we're not going to type anymore. Lesson learned. Anyway, so I don't know if you noticed, but I just queried an Excel file. Right? I didn't do anything special. I just said, query data.xlst. XLST, of course, I switched the two letters. OK, XLSX, whatever. And I just kind of understood that I meant Excel, and it loaded the right driver, and it queried the Excel file as if it was a table. Right? And what we can do, of course, is take that and create a database table from the file. So now we have a table, T, which contains the data from our Excel file. Now that we have a table, we can, for example, copy the result of the table, or copy the table memory into a different file. How does it know that it's going to create a JSON file? It's looking at the name of the file and says, oh, it's .json. Let's create a JSON file. Let's check that it actually did that. Yep, same data in the same file. It's that easy to actually move around. And you can, obviously, if the file was a gigabyte or 10 gigabytes, it will still work, just take a bit longer. Now that we have the JSON file, we can just make a table out of it. We can also make a view out of it. Show table list. Thank you. There we go. So we can move data around. By the way, the difference between a table and a view is a table actually contains the data, so we copy the data from the file into a table in a DuckDB format, and the view just stores the query, and then when we query the view, it goes to the original file and queries from the file. And of course, we can copy into, and this is, I think, the coolest demo, because this is one of the things that always annoys me, that you can't actually create an Excel file from the data that you're working with, and DuckDB can actually go and create, surely, did I make a mistake? No. Oh, because we don't have a, no, that's correct. I messed something up. Oh, I know why. No, J exists. It's this one. I didn't load the Excel driver. There we go. And so we now have, let's find it somewhere, our Excel file, and it contains the same data. So I just exported it into an Excel file, which I know it sounds silly, but like, oh, you moved one row around. But those are the things that would take people like me hours to actually take the result of some Python application and store it in an Excel file so I can send it to someone else. And this just works, right? I can do the same query in a Python application or in a C or a C++ application, any application where I can just run the same query in my application, and it will just go and create the Excel file. I don't need to load some driver and know how to work with the library for creating Excel files or any of that stuff. I can just import DuckDB, run the query, export or copy to the name of the Excel file, and it just worked. So this, I think, is one of the cooler ways you can use DuckDB, which is just moving data around for pretty much any purpose you want. Now, this isn't special. Like, this is not like a big data thing. It's just a very convenient way to actually consume data from one place and put it in another place. OK. But now let's talk about more big data-ish stuff. Without going into too many details, but normally when we store a lot of data for analytical purposes, we don't put them in JSON files, or we don't put them in CSV files, because it's very expensive computationally to query a CSV file. If you want to just query a bunch of data that lives in a CSV file, let's say you have a 1 gigabyte or 10 gigabytes of CSV data, or JSON data, wherever, to actually query it and like analyze the data, you actually have to read the entire file. You have to go through every byte and then parse it, which is a CPU computationally expensive operation, and then extract the data and run it in memory. That's why over the past 10 years, we invented a bunch of different formats which are more optimized for queries, for actually analyzing data. They're all called columnar storage formats. The two most popular ones are Parquet and ORC. And what they do is, when you store the data, they create the file in a way that's actually more optimized for queries. Specifically, they create files that store the data of every column sequentially. Normally, in a database, right, how do you store data? Every row, every record is stored sequentially on disk. And so if you want to read the entire record, the database can read it very quickly, because especially on a magnetic disk, it will just read the entire sequence of bytes. But if you want to analyze, let's say you want to sum all the values of one particular column in a database. When you're storing every record sequentially, to find the value of one column, you have to go and read that column, parse it, and get the value, read next column, parse it, and so you end up doing a lot of disk I/O, which is completely wasteful. And so columnar formats, what they do is they turn it around. They store all the values of one column sequentially, and then all the values of the next column sequentially, and so on and so on. And so if you want to return the record, that's very computationally expensive, because you go to a bunch of columns and retrieve the values. But if you want to do math on a single column, you do aggregations on one column, that's super easy, because you just read the bytes sequentially, and you aggregate the column. And so columnar formats are specifically meant to address analytical aggregation queries. And that's what they do. They take all the different records, they compute all the columns, they also compute a bunch of statistics and pre-aggregate a lot of the data in advance. For example, at the end of every column, we store the number of items in the column. So if we want to count them, we don't need to count all of them. We can just read the 2 bytes at the end, and that's the count. And they store minimum and maximum values. They store the sum if it's numeric. And so columnar formats do a lot of the heavy lifting for us and store the answers in advance. And then when we query columnar formats, we don't need to read the entire file, which is usually where the heaviest part of the query comes, right? It's not the compute and memory. Usually the part that takes the longer in analytical queries is just reading bytes from disk. And so columnar formats let us read a lot fewer bytes from disk, and the query runs much faster. So let's take a look at a few of those. Unfortunately, I have to close this thing every time because Windows. OK. So this is just a Parquet file, like I said, a columnar file that lives somewhere in GitHub. And we're going to create a view on that Parquet file where they have a table named view. So what we're going to do is we're going to close and open there we go. OK. So we created a view. The view doesn't actually bring the data, right? So when I query the view, it will actually bring the data here. If we create a table, this will actually go and read all the data into DuckDB in memory or in a disk file, and then load it, and then we can query it as well. So let's take a look at the difference in query times between a view and a table. You'll notice that this is just a file somewhere on the internet, right? It's not a database that lives on my machine. But OK, obviously, the reason it's taking so long is because it's reading all the data from the file. Hopefully, the internet connection here is going to be good enough to actually finish the demo, because otherwise, we're going to be waiting for a while. Probably should have picked a smaller file. OK. So when I go and select count from a view, what it does now is actually goes and reads the file from the internet. When I do it on the other table, on table L, because we already loaded data in memory, it runs much faster. So you can see this took 5 seconds because it actually had to go and query the data from the file that's remote. And this went and queried the data locally. Now, one isn't necessarily worse than the other. There's 2 different ways to work with data depending on where the data lives. If all of your data in your company, in your organization, lives in S3, in some data lake, then you don't want to load all of it necessarily into your laptop. Maybe you want to read it remotely and just work with it this way from your laptop. Maybe you just you have a specific subset of data you want to work with, and then it makes sense to take the remote data, load it into a local table, and just run a bunch of queries on it, and that's going to save you a bunch of time. So you have both ways, right? And they're going to be used in different use cases. And so as you can see, obviously this takes much faster because we already loaded the data into a table locally. So the cool part is, this is just a random file. This Parquet file is a public data set of the New York cab company, which stores all the different trips that you took, and just expose it as a public data set. And if we do select count, you notice that this ran kind of suspiciously quickly. It's a remote file, right? And we did select count from this file, so it should count all the records. This file, from experience, I know it's like 50 megabytes. So there's no way we actually transferred 50 megabytes in like less than a second to my machine, right? So what actually happened? The magic here is, if you want to know what happened in the query, let's do explain analyze. And the magic happens actually here. It gives us statistics on the HTTP. And you notice that it actually only read 10 kilobytes. So how did it count all the records in this 50 megabyte file that lives on the internet by just consuming 10 kilobytes of data? So the way it works is, and we can actually kind of get a hint from what it did. Obviously, it did the head file to check if the size of the file over HTTP, and then it did 2 get operations. The first one was to get the header of the file, to understand where the columns are, and the second get was to go to the end of the column and get the count, because it's already stored in the Parquet file. That's the cool part about Parquet files. Instead of reading 50 megabytes from the file over the internet, we actually read 10 kilobytes because we just went to the right place in the file and got the count. If I wanted to do min or max or average, it would be more or less the same, right? Because it's already pre-computed for us in the columnar format. And DuckDB knows how to take advantage of that by using the right operations for the right file format, right? If this was a CSV file, then DuckDB would have no choice. It would have to load the entire CSV file and then count all the rows manually. And that would take however long it's going to take. Because it's a columnar format, the engine can take advantage of the columnar properties and actually do a lot of operations very quickly without reading too much. Okay. So let's do the same thing, but with a view. Right, we can create a view. By the way, I can create a view on the whole folder. Like if I have a bunch of files in S3, let's say your company has your data lake or data warehouse lives in S3 or Azure or whatever, and we keep writing new files. So I could, for example, create a view on some path/star or some kind of template where I know the way it works, and then every time we would query, it will go and scan the files and pick the latest files. So I can actually work with a whole folder or like a whole hierarchy of folders and just read all of them. And so this is our view. Our view is just those two files, right? So the view is get all of those. And if we go and run some kind of query on the view, because the view didn't load the data locally, it actually now goes and runs the query remotely. So now we're actually going and doing something more complicated. We're actually doing a where query. You'll see that we actually provided a condition. And so now it goes, and it takes about 5 seconds to load the data. It didn't read all the data. If we tried to read all the data, it would actually obviously take way more than 5 seconds. But again, it works with the data remotely. OK, now for my last trick, what we're going to do is we're going to load a MySQL database. This is just a MySQL database. Show. And there's a bunch of tables in here. Specifically, I put in a table which has all the different values for the previous yellow cab demo we had, right? So the yellow cab table just has the trips. It has a, let's take a look at the actual value. Sorry, this one. So for every trip, that's going to take a little second. I should have done select star. Never do select star. This is an important lesson for everyone here. We're going to regret this. OK. And so it has a bunch of, for every cab trip, like we have the vendor code, where it went, and how long it took, and so on. But we don't have the vendor information. So it just gives you the vendor name, so the vendor ID. But what if I want to join my remote file with the database, which actually has all the vendor codes, right? Because I just showed you that I loaded a MySQL database locally on my machine that has all the different vendors. So we can actually go and attach to our MySQL. So now for my DuckDB, I just created a connection to the MySQL. And the MySQL database can live pretty much anywhere you want, right? So first of all, we now see that the table exists. We can connect the table. We can actually select from. So now we actually can run select queries on the MySQL database. But the cool part is we can do a join between our view, which points to a bunch of files in cloud whatever its names, on S3 essentially, and join it to the table in MySQL. Of course, I screwed something up. Oh, right, this way. There we go. So now what it does is it goes to MySQL and runs the query. It goes to the cloud file, runs the query, does the join, and shows us the results. The cool part is, let's take a look at, and that actually works, just so you know. This field comes from the MySQL database. All the rest of the data is coming from the Parquet files that live remotely. So now let's take a look at what actually happens under the hood, right? So what it does is it takes the predicates, so the where conditions that are relevant to MySQL, and pushes those where conditions to MySQL. It takes the where conditions and all the predicates that are relevant to the Parquet files and uses the optimization in the Parquet files to actually query the Parquet file efficiently, brings the minimum amount of data back, and then joins the rest of it in memory. So you can see that, for example, this is the table scan on the MySQL, right? So we're looking at the vendors table in MySQL. We have a filter where ID equals 1, and so it brings only one row from MySQL. So the amount of data we transfer over the wire from MySQL is very small. It goes to the Parquet file, and of course only reads the minimum amount of rows we need from the Parquet file as well, then brings both of those into memory, and then it does a hash join in memory on the subset, on the sub data sets, and of course then does all the other stuff and shows us, right? And you can see that it actually read in a lot of the Parquet file, unfortunately, but still less than the total size. And if we look at the same thing, but joining it on the work, where the work condition is now on just on the view, and not notice. I don't know if you noticed the difference. The previous query was the work condition is on the view. On here, we're going to put the work condition just on the Parquet files. So we're not going to put the work condition on the MySQL database. And what's actually going to happen is, because the work condition is on the left side of the join, on the taxi table, which is a view that points to the remote file, it's not on the MySQL, what's going to happen is it's going to bring more data from MySQL because it's not pushing the predicate to MySQL. There. Now it's getting 4 rows. It reads the entire table from MySQL because the work condition doesn't say where the MySQL table equals 1. It says where the Parquet table equals 1. And so now, by changing one small thing, instead we're now bringing more data from MySQL, but now we're bringing less data from the Parquet file, right? And so now we're actually only reading how much was it? Still the same amount of time, but we're bringing in fewer rows. Instead of 18,000, we're bringing 4,000 rows from the files, but we're bringing more from MySQL. Now I could actually do the last thing, which is where t equals it, and what was it? What was the last condition? So now I have the same predicate. It doesn't make any difference in the query, right? I'm just adding it apparently for no reason. But because I'm putting the condition both on, we spammed the cloud provider so much, it blocked us. Important lesson. But if they didn't block us, this would actually work. And what we will see is it will only get 1 row from the MySQL and 1 row from the cloud file. So the point I'm trying to make is that it's much more efficient when you actually push the predicate, the condition, to the source where you're actually reading. And DuckDB knows how to work with pretty much any data source. If we're working with MySQL, it will go and push the predicates to MySQL. If we're working with Parquet files, it will take advantage of that. So last demo, which is, sorry, this one. The one use case that I really like DuckDB for is running very quick ETL, extract, transform, load, so data transformations. ETL is like it's a big deal in the data world, and trying to transform and move data from one format and one data source to another is always tricky, and there are very few easy ways to do it. You have to either learn some tool like dbt or some framework for ETL, but if you just want to do something very quick, let's say I have a bunch of CSV files from my customers. They upload a bunch of data to my, to S3, and every now and then I want to take the CSV files every hour and compress them into Parquet format so I can query them very quickly. I don't want to spin up a whole ETL process just for that. I want to do something very easy. And so if you want to just do very quick and dirty ETL, so extract, transform, load on data, we can do that with DuckDB very easily. So let's take a look at the simplest way to do ETL. Okay. Let's say we have a bunch of CSV files, like this CSV file, lineitem.csv. It's a 7.4 gigabyte file that, let's say, our customers upload to us every so often, and we want to turn it into some useful representation that we can query later. So with DuckDB, all we do is, from the command line, right, we tell DuckDB, select from CSV, and then copy it to this Parquet file, just like we did earlier. Then it's going to run for a little while. And in a couple of seconds, it will actually take those 7 point whatever gigabytes and then transform those into our Parquet file, which is OK on itself. I'm going to let it run to the end and see. In the meantime, I'm going to prepare something else. Let's hope this works, and they have actually unblocked us because they usually time you out for a couple of minutes. This is going to keep running. But what we just saw is we can do a select query on a file into another file in a different format. It's one command. Like I could now write a cron job, which does this command every hour on my CSV folder, and then just pour that into my S3, data lake, whatever it is. And that's the simplest way to do ETL between any number of different file formats. I can see that other people are finishing. We have 30 seconds to finish, I promise you, because it's still running. Like, next time I'll get a better laptop with a bigger hard drive. And so in the meantime, we can look at the other demo, which is we're going to just get some fields from, I'm going to make it bigger. Oh, there we go, it's finished. And we can see that we created our Parquet file. There it is. It's, of course, much smaller because Parquet is a much more compact format. And we just did our ETL very quickly. Last thing, let's say I want to extract some data from our data lake into a JSON file or CSV file. All we have to do is query, so select from this remote file into this local JSON file. And let's hope it actually works. Nope, we're still blocked. But if it did, what would happen is we would actually get the cab rides with just the right fields in the JSON file locally. And we can do that from pretty much any data source into any other data source, right? Let's say we have a MySQL database. I can select from MySQL into a Parquet file in S3. Or I can select from S3 into MySQL or any other transformation. I can do it from the Python application. And so like the combinations are endless. OK. Just to summarize really quickly, and then if you actually want to ask questions, you can ask questions, but otherwise we'll finish. Should you run out and download DuckDB right now? Obviously, yes. But are you going to use it at work tomorrow? Probably not. But I just wanted you to have this in the back of your mind so that if you run into some data operations you want to do, and you don't want to spin up like an EMR cluster or Spark or learn whatever, DBT, you can just do this very quickly with just basic SQL knowledge and one file. Anyway, we're done. Thank you very much for listening to me. Enjoy the rest of the conference.